So we don't really have bigger brains for the most part than all other animals, and we don't have more cells per se relative to body size, but what we do have is we can activate more cells to work together at the same time because we have this precise timing mechanism in our brain. But we don't start out with that timing mechanism. We have to grow it and develop it, and we grow it and develop it in either side of the brain independently, but they eventually merge together. So what happens is that as the child's born and as brain cells interact with the environment and genes get turned on, the brain starts to grow in this real rapid way. And as it grows, the left side and the right side are growing independently of one another, but then they start to intermingle and they start to develop connections. Especially as they mature, they develop these long-range connections that link certain networks on one side to other areas of the brain and coordinate the brain to work together and work in a very unified, rhythmic way. When this breaks down, it produces a big problem. So what we see in a functional disconnection and what we see in epigenetics is that the genes that are affected are the ones that are building these connections and coordination in the brain. Why are those genes specifically affected more than other genes, meaning that environmental factors are turning them off? Because they're 85% of the genes that we have. We have roughly 25,000 genes in all of our cells. 85% of those are there to build our brain. These are the brain cells that are these are the genes that are the most sensitive to environmental influences. And so those are the ones that can be impacted positively or negatively if we don't stimulate them at the right way at the right time. Now, what also seems to be happening is that in this problem, as the child is developing, normally the brains develop at the same time and coordinate. They start to increase their speed. So essentially think of it that each year in development, both sides of our brain get an upgrade in our processing speed. So just imagine if each year we were getting an upgraded processing chip. And each year our brain could process faster and faster and coordinate more areas of the brain to work together. But what's happening in a functional disconnection is that one side of the brain is getting this upgrade and the other side is not getting as much of an upgrade as fast. So what would happen if you have a new computer and an old computer with completely different processing speeds? Both worked, but you put them together with wires and connected them. Could they work together and share information? And the answer is no. And you say, why? Well, it's purely because they have a different processing speed, not because they're broken, not because there aren't connections, but just simply the timing is too different. And that's what happens in our brain. We have one side of the brain that is slower than the other. It's not maturing at the same rate. It's not damaged or broken as far as we can tell. It just isn't maturing and growing that fast. And this creates an imbalance in processing speed that doesn't allow the brain to be able to coordinate and bring all these different areas together. Now, why would that happen? Why would one side of the brain develop at a slower rate than the other? Why wouldn't they both be slow? Well, because both sides of the brain don't normally develop at the same time. That the right side of the brain develops in the womb and for the first 2 to 3 years of life, and then the left side of the brain develops for the next 3 years. Then we get the right side of the brain again for the next 3 years, and back and forth every 2 or 3 years until we're adults as far as we can tell. So what we're seeing is that the problem is that environmental factors are impacting and affecting genes from turning on at specific stages of development. The genes that are most impacted are the ones that build connections in the brain and help the brain to grow and coordinate. If these environmental factors happen at a specific window of development, they will affect either the right side of the brain from developing in the first 2 to 3 years, or the left side from developing more than the right in the next 2 to 3 years. And this can lead to a specific imbalance physically and coordinatively, and this is what a functional disconnection is. But the makeup of that, what areas of the brain are growing too slow and what areas of the brain are growing faster, and superimposed on the child's natural abilities and traits. What we see in general is that the children that are most susceptible are the ones that are most gifted. If you look at the other siblings, and this has been documented, that children with autism, their siblings are usually off the chart with intelligence. Same thing in families with ADHD and OCD. If you see children that have dyslexia, what we see is their spatial intelligence is usually unbelievable. Their social intelligence and emotional intelligence is usually extremely high. And what we also see is that what we see in the children with their gifts is usually what we see in the parents. That children that have dyslexia and learning disabilities typically have parents that have extremely good right brain skills and are extreme right brain individuals. We see children with ADHD and autism and OCD and Tourette's, they're the opposite. The parents have extremely high left brain skills. And what we see is that we can see that in the profile. So that one of the things that also doesn't seem to make sense to people from the outside is if you look at autism and ADHD, as you go up the socioeconomic scale, if you look at the more money you make, the better educated you are, the better schools you went to, the better job you have, the better neighborhood you live in, the more likely you are to have a child with autism or ADHD. Doesn't seem to make sense, but that's clearly what we see. And we know that it's not because they have access to better health care. It's because of the makeup of the parent. Those parents that are likely to have children with ADHD, the most common job in the majority is an engineer, or they work in the IT industry. They're very technically savvy people. They're extremely left brain intelligent. Whereas we see, people with dyslexia, their parents may have extreme right brain skills. They're very social, they're very emotional. They tend to be in jobs or they may be top athletes, professional athletes, or people that are very good, speaking in public, or very social and, very communicative. So we see that all of these things come together that creates this issue. But the good news is that we can change it. Now, the other thing that makes the human brain unique is that we have the right and left side of the brain are completely different than one another. Humans have the most what we call asymmetric or lateralized brain. The two sides of the brain are very different. Both sides of the brain can do everything. So in the past, we used to hear that the left brain only did this and the right brain only does that. That's not true. But what we do see is that there's a clear difference in what they're specialized in. So that the left hemisphere has all of these centers on the side that it's really specialized in, and the right has the opposite things that it's specialized in. Like the left side is verbal communication, the right side is nonverbal communication. But to have a normal conversation with anyone, you need both happening at the same time, right? So we hear it's not what you say, it's how you say it. Well, the what you say is the left brain, and the how you say it is the right brain. So if we have too strong of one or too weak of the other, it's going to affect our ability to communicate to other people. So what we see is we have all these different centers, and we can mix and match them in really unique and cool ways that no other animal can. But the key to that, again, is that we need to do it at the exact same moment of time. That we can't do this in series, meaning we can't light up one area and then another area and another area and another area. We have to do it in parallel. They all have to light up at exactly the same moment. Not even close, but the same. And if there's even maybe hundreds of milliseconds or nanosecond difference between when they light up, they can't communicate and synchronize with one another. And we believe that's partly what's happening. And that's also why it may be so mysterious, because we don't really have ways of measuring the brain at that speed. We don't really have ways of looking at the brain on the nanosecond time scale, readily right now. It's very difficult. So what we